Okay, so now that you have a little bit of a background about matrices and that they're just often just used to represent an equation or a system of equation, let's think about how can we use a matrix to help us solve these systems, as if we were solving them and they had the variable still there. So there are three row operations that we need to define. Okay, so the three kinds of row operations. Row operation kind number one is that you can always multiply the entire row by a constant. So you can always multiply the entire row by a constant. And so if you think about, like, for example, if you had, like, let's say an equation like 2x plus 3y equals 10, and you just multiplied everything by 5 for whatever reason, then you'd have 10x plus 15y equals 50. Like, those are equivalent. So you really haven't changed your equation. You just represented it with different coefficients. And a lot of times, like, you might be trying to get a single variable by itself. Like, maybe we multiply everything by 1/2. So another equivalency would be x plus 3 over 2y equals 5. Again, so you multiply the entire row by a constant. And each of the rows will be numbered like 1, 2, 3, like top down to bottom. So there's going to be something that I'm going to call like row language. Like, what row language or what row symbols are you using? So if you multiply something by a constant, you'd say, oh, I'm multiplying 2 row 1, or I'm multiplying row 1 by 2, and I'm just going to leave it in row 1's position. It becomes the new row 1. Or if I multiplied 1/2, maybe it was in row 5 or something like that, or row 2, 1/2 row 2, I'm going to leave it into row 2. That's the new row 2. So this is what I'm going to refer to in terms of like a row operation language, or like what is your operator here? Like, give me an idea of what you're doing in your steps. Okay, so your next row operation is that you can switch rows. Okay, so you can do a row swap. And really, I mean, think about like what would that represent if you had an equation like 2x plus y equals 10, and you had 3x minus 8y equals 1, and all of a sudden you just rewrote them like, oh, put this one first, and then this one, for whatever reason you want to do that. Okay, you're just switching out row 1 and row 2. You haven't changed anything. And sometimes it's nice to switch those rows around. And so what you're doing is you're doing row 1 swapping out to row 2. And so that's it. You just write that language there. Okay, and then the last row operation is what I like to call like a linear combination. Okay, and so then a linear combination is where you might, let's say you take these two rows and like you might want to multiply this top one, right? Like I might want to multiply the top one by 8 and then add it to that one. Because if this were an 8y, 8y plus a negative 8y would be 0. Right? And so that's how we would solve these equations. So if I want to do a linear combination, what I might say then is I would, like, as an example, I should say, like I might say, oh, I might want to do 8 row 1, I want to add it to row 2 because I want those to cancel, and then I'm going to put the result into row 2. So that would be an example of a linear combination. And so again, like my row 1, I wouldn't have changed. I would just have left it as like a 2x plus y equals 10. But now this row 2, I'm going to change, right? What I'm going to do is I'm going to follow this operation. I'm going to take 8 times this whole thing, and then I'm going to add it. So like 8 times 2 would be 16, and then 16 plus 3 would be 19x. And then 8 times y would be 8y, plus a negative 8y would be 0y's. And then 8 times 10 is 80, plus 1 is 81. So I still have 2 equations here. I've just kind of transformed that last one by doing 8 times the first row and then adding it to the second row and putting it into row 2. So those are our 3 row operations, and we're going to come back to those and reference those, and that really is going to become the basis of how we're going to start solving these things very efficiently. Okay, so it says, okay, like now again, this first example says, are these systems equivalent? And so if I look here and I say, oh, wait, oh, look at this. They both, these, right, they both, first of all, have 2x plus 4 equals 8. 2x plus 4 equals 8. So that's true. And then look at that first equation. Like, it's really close to this equation, right? If I just multiply by 2, I'd get from the first row, the first column, to the second column. So I would say that, yes, if I call this system 1, and this system 2, and this system 3, 1 and 2 are definitely equivalent. Because to get from 1 to 2, what I'm doing is I'm taking 2 row 1, and I'm putting it back into row 1. I'm just doubling all those coefficients. Okay, now, oh, and then look from row 1 over here to row 3. What's the difference? The rows are just swapped, right? So those are equivalent because row 1 was swapped with row 2. So yes, they are equivalent. And this would be the transformation you'd use, that you could represent the transformation using row operation language. Okay, so now, next one. Are the next ones equivalent? So looking here, I notice there's an x plus 3y equals 5, so those are the same. And now this one here, let's see, it's not a scale multiple, but I hope you realize that, look at this, x plus 2x, that's 3x. 3y plus 4y, that's 7y. 5 plus 8, that's 13. Aha. So that's a linear combination. You're taking row 1, you're adding it to row 2, and then you're putting it into row 2. So if I think about, I'm doing row 1 plus row 2, and I'm going to put the new result into row 2. And remember, this is the new result. This is the new one. And so therefore, it's going to be the one that's changed. Right? So row 2 will be changed. Row 1 will not be changed at all. So like that's why row 1 stayed the same as this, but now the row 2 has been changed to represent the sum of the 2 rows in the new in the new row 2's position. Okay, now going from here to this one over, like again, still row 1 is the same, but now look at this. There's a 7x, a 19y, and a 38. And so if I think about, how am I going to get this? Well, let's see. If I multiply, again, thinking about like kind of like a linear combination, if I multiply this x by 4 and add it to 3, I get 7. If I multiply 3 by 4 to get 12 and add to 7, I get 19. And if I multiply this 5 by 4 to get 20 and add it to 13, I get 33. Oops, I think there's a typo here. I want to multiply these by 4. So that is my bad. I thought I had that fixed. So change this 38. Change that. Sorry about that. Change that 38 to pretend it's at a 33. Because now when I take that times 4 and add it to 13, I do get the 33. So row operation, what would that language look like? So what I did is I did for row 1, I added it to row 2, I put the result back into row 2. And again, thinking about like if you multiply that by 4, right? So you'd have 4x plus 12y equals 20, and you add that to 7, you add that to 3x. Oh, my eraser's not working. There we go. You add that to the 3x plus 7y equals 13, and you would get 7x plus 19y equals 33. So this right here is the new row 2. And that's exactly what I had right there, if I didn't make that typo, where the first one stayed the same. And again, to emphasize this one more time, because I'm just thinking about sometimes what students might make by mistake, by accident. Like notice I multiplied row 1 by 4, but that does not affect your original row 1. that is just, oh, I'm doing 4 times that row 1. I'm going to put it to row 2, and now my result is the new row 2. So that's the only place that gets changed. Your first row would not get changed at all. Okay. And then let's maybe I guess, yeah, let's go ahead and finish out this one right here. Example 2 says, what row operation would take this system down to this system? So if we think about, okay, so like there might be several things that might be happening. I'm noticing that I want to maybe get this 0 here, and right now there's a 2. So if and I also notice that the first row isn't changed. So what I might be thinking about is there something I can multiply row 1 by, right? So is there something that can multiply row 1 by, so that when I add it to row 2 and then put it back into row 2, I get a 0. And so again, thinking about linear combinations, right? If these were opposites of each other, that'd be perfect. So if I did -2 row 1 and added it to row 2, and put the result into row 2, that would definitely give me a 0 here, right? Because and again, thinking about like this coefficient, so 2 times 1 is 2. Sorry, -2 times 1 is -2, plus 2 would have given me 0. Now, does that work with the y's? So if I do -2 times 3, right, is -6. If I add that to 4, I get -2. Aha, very good. If I do -2 times 5 is -10, plus 8, -2. Yes. So what I can do is I can record this as sort of like my work. Like that's what's allowing me to transform the given matrix, or I guess the given system, which I could use it as a matrix, to go from there to here. Because once I get it here, look at how nice it is. We know how to solve for y. Y would have to be 1, and then you go back and figure out that x would have been 2. Okay. And then maybe thinking about example 4 here, it says, well, what row operation could be used or should be used to transform this into a simpler one? And when I say simpler, maybe it's going to get rid of x or get rid of y. And so kind of maybe, again, thinking about like a systematic way to solve for one, I might look for ways to cancel out variables. And so I've noticed there's a y and a 3y. So if I could get those opposites, that would allow those to cancel. So maybe that would be a good thing to do. Maybe I want to do -3 row 1, add it to row 2, and put the result into row 2, because that would make these opposites. So then my notice row 1 will not be changed. So I would still have 3x plus y equals 4. Only row 2 is changing. So do -3 times 3, which is -9. Add it to 7 is -2. -3 times y is -3 plus 3y is 0. So that was exactly what I wanted to do. And then -3 times 4 is -12, plus 16 is 4. So right now, I still have 2 equations, but this one tells me that -2x plus 0 equals 4. Oh, that means x is -2. And once you know what x is, you can always go back and substitute it into the other equation right there. So 3 times -2 is -6. So now I have 3 times -2 is -6, plus y equals 4. So -6 plus y equals 4. So y is equal to 10. And so my solution would be -2, 10. And you could put -2, 10 into this equation or into this equation, and you'll get the same answer because we found the one solution. It's a consistent system that we found one solution. So again, this video, just trying to get us used to the different row operations, and thinking about how can we use them to represent transforming a system into a more simplified system by getting rid of or eliminating variables. And honestly, like that's all we're doing is in algebra, we're solving. So when there's multiple variables, we try to eliminate them. We're just trying to come up with a systematic way to do this. And initially it may not seem systematic at all because it's new, right? So it's gonna take some time to get used to doing it in this fashion.